In the previous lesson, we began talking about polynomial functions in general, and we referred to a few facts about their graphs. In this lesson, I want to take this graphical discussion much further. My hope is to develop a number of general principles or tools that we can use whenever we want to draw the graph of any polynomial function. One thing we can say is that the graph of a polynomial never breaks, and it never has a sharp corner. The fancy mathematical phrase for this never breaking is that a polynomial function is always continuous. But you don't have to worry about that phrase for now. In fact, you won't really need to worry about continuity until you get to a calculus course. So, for example, here are the graphs of a few polynomials, and I want you to notice that these don't break and they don't have a sharp corner. For example, here's the graph of x cubed minus 3x squared plus 2x plus 1. It's a nice smooth curve, goes up, comes down a bit, goes back up. No breaks, no sharp corners. Let's look at another. X to the fourth minus 5x squared plus 2x. And again, notice that we've got some curvature to it and so on. We've got some parts that are going down, parts that are going up, but no breaks and no sharp corners. This is the important point for now. How about another? Let's take a really complicated looking polynomial. 1 over 200 times x to the sixth minus 29 divided by 200 times x to the fourth minus 3 over 25 times x cubed plus 43 over 50x squared plus 6/5 x. Okay? That's a pretty complicated polynomial. Maybe the most complicated one we'll see in the whole course. I don't know. But notice its graph. Even though the polynomial is such a mess, the graph never breaks and it never has any sharp corners. And this is important because every polynomial will have those two properties. I think that's a pretty cool looking graph, to be honest with you. But now I want you to compare the graphs that we've just seen with graphs of some things that are not polynomials. So, for example, let's take a pretty straightforward function. X raised to the 2/3 power. Now, this is not a polynomial. Do you remember why? Remember, the powers, or the exponents as we call them, on all the powers of x, on all the variables x, need to be positive integers. And 2/3 is not a positive integer. So x to the 2/3 is not a polynomial. Notice that sharp corner right at the origin. If you look really, really carefully at what's happening close to the origin, you'll see that it's not a nice smooth U shape. There's actually a corner that's coming in, a sharpness that's happening right at the origin. No polynomial graph would ever do such a thing. Let's look at another function. X squared plus 1 over x squared minus 1. Now, this is also not a polynomial. Remember, I said in a previous lesson that almost always, if you take one polynomial and divide it by another polynomial, you will not have a new polynomial. And that's the case here. X squared plus 1 over x squared minus 1 is not a polynomial. And notice its graph. It's actually in three distinct pieces. There's a piece up in the first quadrant, a piece up in the second quadrant, and then there's this sort of U shape down at the bottom. Those three pieces are broken away from one another. And so if I walked up to you with that graph and showed it to you and said, could this be the graph of a polynomial? Your answer would immediately be no, because no polynomial graph will have pieces that are broken up away from one another. Okay, so we know that the graphs of polynomial functions are going to be nicely behaved. There are no breaks. There are no sharp corners. Everything is going to be nice and smooth throughout the entirety, the whole graph of a polynomial. Now, let's remember what I said at the end of the previous lesson about polynomial functions in general. First, the domain of any polynomial is the set of all real numbers. That, by the way, is part of the reason that you don't have any breaks in the graph of any polynomial. And secondly, the range of a given polynomial depends on its degree. If the degree is odd, then the range is going to be the set of all real numbers. And if the degree is even, then both ends of the graph are going to go in the same direction. They'll either both point up or they'll both point down. And because of that, the range is restricted. You might even look back at the polynomials I showed you just a few minutes ago to see what happens whether the degree was odd, in some cases it was there, or the degree was even in other cases. So every real number is in the domain of any polynomial function. You're allowed to plug in any real number you want into a polynomial. This is very important. It's not true of some other functions that you know. For example, you cannot plug x equals -2 into the function f of x equals 1 divided by x plus 2, because that would cause division by 0, and division by 0 makes no sense. So x equals -2 is not in the domain of f of x equals 1 over x plus 2. But of course, 1 over x plus 2 is not a polynomial either. Similarly, if you want the output of a function to stay in the real numbers and you don't want to include complex numbers, then the number x equals -5 is not in the domain of g of x equals square root of x. Why? Because square root of -5 is not a real number. So that's another example, square root of x, where the domain is not the whole set of real numbers. But square root of x is not a polynomial either. Any polynomial, no matter what polynomial you choose, is not going to have problems like division by 0. It's not going to have problems like having a negative number under a radical symbol. Every real number you want to plug in will be in the domain of a polynomial function. So that's very important. You can actually plug in any value you want. And from a graphical perspective, for a polynomial function, that means that there aren't any gaps in the graph. There are no parts of the x-axis where the graph somehow disappears or breaks apart. And that's very, very important as you get ready to graph a polynomial. Okay, what else can we say about the graphs of polynomials? We've said several things already, but there's actually more that we can say as we walk through these ideas about graphs of polynomials. We can talk about the number of x-intercepts of a polynomial. And it turns out that the number of x-intercepts of a polynomial depends on the degree of the polynomial. In fact, the number of x-intercepts of any polynomial you choose is at most the degree of the polynomial. I'm going to talk about this more in some later lessons, but for now, just trust me on this as we want to talk about these graphs. I want to be able to use this fact. The number of x-intercepts never has to equal the degree. In fact, sometimes it does, but it's not required to be equal to the degree. It's just the case that the number of x-intercepts needs to be less than or equal to the degree of the polynomial. So, for example, here are the graphs of several polynomials of degree 4. I want you to notice that you could have 0 x-intercepts, or you could have 1 x-intercept, or maybe 2 x-intercepts. You could even have 3 x-intercepts for a degree 4 polynomial, or you could have 4 x-intercepts. Here are some examples. Take f of x to be x to the 4th plus 2. This is a degree 4 polynomial, and it has 0 x-intercepts. The graph lives completely above the x-axis. Okay. Take a function like f of x equals x to the 4th. Now, this is also degree 4 polynomial. It's also a monomial. Remember that language from the previous lesson. And f of x equals x to the 4th has exactly 1 x-intercept. It's the origin. No problem there. Take f of x equals x to the 4th minus 2x squared plus 1. It's a perfectly gentle 4th degree polynomial. In that case, it would be a 4th degree or quartic trinomial because it has 3 terms. And x to the 4th minus 2x squared plus 1 has exactly 2 x-intercepts. Okay? Take another one. Take f of x equals 2x to the 4th minus 4x squared. Also a quartic polynomial, a degree 4 polynomial. In this case, a quartic binomial, and it has exactly 3 x-intercepts. So now I've shown you quartic polynomials that have 0, 1, 2, or 3 x-intercepts. Now take something like f of x equals 2x to the fourth minus 4x squared plus 1. And in this case, you'll now have 4 x-intercepts. So now I've shown you some examples where you could have anywhere between 0 and 4 x-intercepts for a degree 4 polynomial. They can range. You can have any of that you want. But I do want to point this out. I would never be able to have 5 x-intercepts for a degree 4 polynomial. So this gives me at least some sort of boundary, if you will, on the number of x-intercepts I'm allowed to have. I can have anywhere from 0 up to the degree of the polynomial. And that's helpful if I want to start graphing a polynomial. Now, a little bit more can be said about these graphs of polynomials. So for example, the ends of the graphs of a polynomial never flatten out. They never go to the point where they can't get above a certain y value. They keep going on, either going up to plus infinity or going down to negative infinity. Maybe both go up or both go down or one or the other, but the ends can never flatten out. So they must go up to plus infinity or down to negative infinity. Also, if the degree of the polynomial is even, then either both of the ends go up or both of the ends go down, sort of like a parabola. Remember, degree 2 polynomials or quadratic polynomials have parabolas as their graphs, and both ends of a parabola either go up or they both go down. The upness or downness, if you will, is determined by the sign of the leading coefficient, just like with parabolas. So if I'm looking at, say, a degree 4 or a degree 6 or a degree 8 polynomial, all of which would have even degree, the ends of those polynomials will either both go up or both go down, depending on the sign of that leading coefficient. Now you can see why I cared so much about the leading coefficient. If the degree is odd for any polynomial, then one of the ends is going to go up and the other end is going to go down. And the sign of that leading coefficient is going to tell me whether the end on the right is going down and the end on the left is going up, or vice versa. Now, it's important then that you keep in mind the degree of the polynomial, whether it's even or odd, and you look at the sign of that leading coefficient, because those two facts are going to tell you something about what's happening to the ends. And I have to make this point very clear. What I just said about the degree of the polynomial and the sign of that leading coefficient only tells us something about the ends of the polynomial. There might be all sorts of things going on in the sort of middle of the graph of the polynomial. All we know from the degree, whether it's even or odd, and the sign of the leading coefficient is what's happening on the ends. But that's still helpful. If you really want to know what's happening on the sort of edges, so to speak, of the graph, those two facts will help you tremendously. The hard part, really, is what's happening in the middle of that graph. Now, how is it that we really know for sure, with certainty, that the end behavior that I just told you about depends on this leading coefficient in such a strong way? Well, it's because the term containing that leading coefficient is what I like to call the dominant term in a polynomial. Now, that's not really an official term, so to speak, but it's a very important idea that I want to talk about for a few moments, because this dominant term, the term that holds that leading coefficient, is really playing the role of deciding whether both ends are going to go up, both ends are going to go down, or one end will go up and the other will go down. Now, let me try to explain what I mean by this dominance of that one term by looking at a quick example. Consider the cubic trinomial 4x cubed plus 9x squared plus 3. When we're talking about the end behavior of a polynomial, we're talking about what's happening to the graph when x is large. And I don't mean x equals 100, I mean something like x equals 100 million, or maybe even bigger, like x equals 100 billion. But for now, let's do this. Let's plug in x equals 100 million into the polynomial I just mentioned to you, and let's do it one term at a time, and let's see what's happening. Now, Stay with me as we walk through this. The first term was 4x cubed. I want to plug in 100 million. Can you imagine how far down the x-axis we are when we plug in 100 million for x? We're way out there to the right. When you plug in 100 million into 4x cubed, you're actually going to get 4 times 100 million cubed, and that's a 4 followed by 24 zeros. Okay, that is a large number. Imagine if you had that many dollars or pennies even. It would be a lot of money. Now, let's take the second term in this polynomial. It was 9x squared. And let's plug in 100 million for x there. And there you would have 9 times 100 million squared. And if you do that, you're going to have a 9 followed by 16 zeros. Now that's also a pretty big number. I'll give you that. A 9 followed by 16 zeros, that would be a very large number as well. Now the third term in this polynomial is 3. And of course that has no x's in it, so the 3 is just a 3. That's what you get when you plug in 100 million. That term is just a 3. Now I want you to think about these numbers for a second. I realize that the first two are pretty big, but I want you to understand that that first number is much, much bigger than the others. It has more zeros in it by far than the second term. So bottom line, that first term, 4x cubed, is going to dominate the other terms when the values of x are huge. So when you actually see what the polynomial equals when x equals 100 million, you're actually going to get a 4 followed by 7 zeros and then a 9 and then several more zeros followed by a 3. You see that that first term, the 4 followed by 24 zeros, is really what made the difference here. Yeah, the other terms played a role, but that first term really is the biggie. It's the dominant one. So it's true that the end behavior, what's happening when the x values are either really, really big in the positive direction or what's happening in the other direction, that end behavior is completely dictated by the term containing that leading coefficient. Now, let's spend a few minutes looking at the graphs of some very specific polynomial functions. And I want to focus some serious attention on the graphs of cubic, quartic, and quintic functions. So let's jump to this example. Sketch the graph of the cubic monomial function that is f of x equals x cubed. It has one term, that's why it's monomial, and it's degree 3, so it's cubic. Now, this is a basic function. It's just one term, but I want to talk about everything we know that we've talked about up to this point about the graphs of polynomials. First, there's just one x-intercept. It's pretty clear. It's at 0, 0. Well, if you wanted to know where the x-intercepts were, and you weren't sure if there were any, or if 0, 0 was the only one, you would have to set the whole function equal to 0 and solve it for x. That's what you do to find x-intercepts for any function. And that means you'd be looking at the equation x cubed equals 0. And now, if you think about it for just a moment, if you took the third root of both sides, and we'll talk about roots later on in later lessons, you're going to just get x equals 0. You could think about this from other directions as well, but bottom line, you're just going to have one x-intercept. It's going to happen at x equals 0. So we have the point 0, 0. We could plot that if we wanted on a piece of graph paper, and we could move on. Now, what can we say about the end behavior of f of x equals x cubed? Well, if you plug in a positive value of x, like something like x equals 10 or x equals 100, what do you get? Well, f of 10 is 10 cubed, which is 1,000. That's getting kind of big. And f of 100 is 100 cubed, which is 1 million, a 1 followed by 6 zeros. So you see that as x is getting large and positive, the y values are also getting large, and they're getting large pretty fast, and they're staying positive. And that means that the part of the graph that's on the right side of the plane, or the right side of the y-axis, if you want to think of it that way, is going to go upward towards plus infinity. Okay? What if we evaluate this same function at negative values of x? In other words, x equals negative 10 or x equals negative 100. Well, let's see what happens. F of negative 10 is negative 10 cubed, which is negative 10 times negative 10 times negative 10, And notice that one of those negative signs is going to survive all the cancellation, and the output value you get there is negative 1,000. So that means that the point negative 10 comma negative 1,000 is on your graph. What if you plug in negative 100, which is even farther out? Well, negative 100 cubed is actually negative 1 million. And that means the point negative 100 on the x-axis, negative 1 million on the y-axis is the point in question there. That means that the left-hand side of this graph is going to behave very differently from the right-hand side. That the y values on this side are now going to go to negative infinity. So one side is going up and one side is going down. Remember, I said earlier, if the degree of the polynomial is odd, one side goes up and one side goes down. That's exactly what we're seeing here. Now, if you just plot some points and connect the dots, and this is always a good idea when you're not sure, plot a few points, connect a few dots, you'll see what the graph looks like. You could have the point 0, 0, we already talked about that. And then if you plug in things like 1, you'll get 1 back. Plug in 2 and you get 8, 3 and you get 27. How about negative 1? Well, that'll give you a y value of negative 1. Plug in negative 2 and you'll get negative 8 back. Plug in negative 3 and you'll have negative 27 back. That gives you a whole bunch of points very quickly. And if you connect those dots, you'll see exactly what you want to see, basically, which is the function y equals x cubed just has this nice smooth shape going down to negative infinity on the left, going up to positive infinity on the right, makes this nice smooth curve that goes right through the origin. Now, let me share a quick thought with you about cubic graphs. Often, people think that all cubic graphs will have a certain S shape to them, as I like to call it, with one hill and then one valley, and then it'll take off from there. Well, it's true that lots of cubic graphs, or lots of cubic polynomials, I should say, have a graph that looks something like that, with one hill and one valley. But it's not the case that they all have to look like that. Notice that the graph of f of x equals x cubed, which you and I just drew a moment ago, doesn't have that kind of a shape. There is no sort of hill followed by a valley and so on for f of x equals x cubed. Part of the reason is because that graph only has one x-intercept, while in some of the typical hill and valley graphs for cubic polynomials, you actually have three x-intercepts. But my point is this. Don't think that all graphs of all degree 3 or cubic polynomials have to have the same sort of shape. It's just not true. And it's not true of all quartic functions, and it's also not true of quintic functions as well. Now, let's use some of the ideas we learned in a previous lesson to find the graph of some other cubic functions. Let's take the following. Sketch the graph of the cubic function g of x equals x cubed plus 4. Well, we know that this graph has to look like the graph of f of x equals x cubed, the graph that you and I just drew a few moments ago. It's just that the graph of this new function is translated by 4 units. Now, do you know which direction? It could be going left, it could be going right, it could go up or down. Which one is it? Well, if you take the graph of x cubed and you translate that graph up 4 units, that will give you the graph of x cubed plus 4. So that graph is actually pretty easy to draw. Okay, let's try to sketch a different graph of a cubic again, but let's try to see it in an intelligent way so that we can draw it quickly. Sketch the graph of h of x equals x cubed minus 3x squared plus 3x minus 1. Now, for some of you, your first reaction is going to be, yikes, that looks really complicated. And honestly, I would agree with you. But I know a little secret, not necessarily something I expect you to know, not yet. And that is this, x cubed minus 3x squared plus 3x minus 1 actually can be factored as x minus 1 times x minus 1 times x minus 1, which is the same as x minus 1 cubed. I promise I'll show you in a later lesson how I got that, but the point is that this function h of x is just x minus 1 cubed. And I know how to draw x minus 1 cubed from the graph of x cubed. Do you remember how to do it? when you replace x by x minus 1 in a function, it means that you translate the graph of the original function to the right exactly 1 unit. So the graph of this h of x is actually pretty straightforward to draw once you know the graph of x cubed. You and I saw that a moment ago. If we now take that graph and just move it to the right 1 unit, then I'll have the graph of h of x, and it'll look something like this. Okay, to close out this lesson, let's look at the graph of a certain quartic polynomial. Okay, so it's quartic. That means it's degree 4. So here's the function I want us to look at. Sketch the graph of f of x equals x to the 4th minus 9x squared. Okay, I'm going to use this as an example to try to motivate some of the things we're going to do in the next few lessons. So just bear with me as we do this. First of all, it turns out that I can factor f of x equals x to the 4th minus 9x squared in a nice way, right? I see that I can pull out a common x squared from both terms. And again, we'll talk about this in the next few lessons. And once I do that, it turns out the factorization of f of x becomes x squared times x minus 3 times x plus 3. For now, you're going to have to just take my word that that's really true. I promise to talk more about how to do that factoring in the next few lessons. It really will come up. But for now, I just want to say this is a fancy example of a difference of two squares that we saw some lessons ago. I promise, though, we'll talk about this more in detail later. Now, what does that factorization of this function tell us? Well, it tells us where the x-intercepts of this graph are. They must be at the places where each of the pieces of that factorization equals 0. Well, the x squared equals 0 exactly when x is 0, and the x minus 3 equals 0 exactly when x equals 3, and the x plus 3 term equals 0 exactly when x equals negative 3. So I actually know that there are 3 x-intercepts here: 0, 0, 3, 0, and negative 3, 0. Remember the rule we had a few minutes ago. Degree 4 polynomial can have at most 4 x-intercepts. In this case, I'm only actually going to have 3. Now, let's talk about the end behavior of this quartic polynomial. Well, I've got to focus on the dominant term. Remember, we talked about this dominant term a few minutes ago. It's the term which actually is the one of highest power. In this case, that's the x to the 4th. It should be clear that no matter whether you plug in a positive number or a negative number for x, the result from x to the 4th is going to be positive. That power of 4, which is even, is going to cancel out any negative sign that's part of the x, because that 4 is even. So even if you plug in negative 10 for x, when you raise that to the 4th power, the y value is going to be positive. And that means that both of the ends of this graph are going to go up, because the y values always have to be positive. Now, we should plot some points now just to see if we can get a picture, if you will, of the general shape of this graph. And this is always a good idea to do. So maybe we could plug in x equals 1, and 2, and 3, and 4, and 5. And maybe x equals negative 1, negative 2, negative 3, negative 4, and negative 5 would also be a good idea. By the way, we already plugged in x equals 0 and found that it was 0. Remember, there's an x-intercept at the origin here. And in fact, you already know what happens at x equals 3 and x equals negative 3 as well. You actually had 3 points already in your pocket. But once you plot these points and you carefully draw where they are on a set of graph paper, on a piece of graph paper, you would have a graph that looks like the following. And to be honest, this idea of plotting points and connecting dots, it might feel a bit childish or easy to do, but it's a great idea, and I strongly encourage you to go through the work of plotting some points and connecting the dots. Now, as I close this example, let me say this. You might be left feeling like we should have had a way to do this, to find this exact graph, if you will, instead of just finding a few special points and plotting a whole bunch of other points. It turns out that there are many other things we could have done to find this graph. But most of the math that you and I would need to apply these tools would actually come from calculus, believe it or not. Things like the derivative. You may have heard some people talk about the derivative if they've taken a calculus class. Those tools are very important for helping us find graphs, and they're useful, but we don't have those yet. That's all right. If you stick with your math, however, when you do get to calculus, you'll see some of these beautiful and very useful tools for finding graphs, and I promise you won't be disappointed at that point. Now, we spent a good deal of time talking about the visual or graphical aspects of polynomial functions in this lesson. Next time, we're going to talk more about the algebra side of polynomial functions, how to combine them in different ways, addition, subtraction, multiplication, division, and something called composition. I'll talk about that then.